Log on, tune in, find out. Another good idea from Cambridge.
Williamson from Oxford will describe some geometric constructions of link homology.
Thank you very much. I'd also like to thank the organisers for this wonderful, wonderful program. I've been here quite a lot, and I think, for example, the introductory workshop was wonderful and the conferences have been really good. So I'll be talking about geometric constructions of link homology. And this is all joint work with Ben Webster. I also forgot to say, I think a lot of people have heard this talk before, but I've tried to make it a little bit different this time. So I first want to say very roughly the idea of link homology. So if we start off with some link, then it's a kind of very well-known story that one can associate polynomial invariance to L. So for example, there's the Alexander polynomial. There's the Jones polynomial. Homflip. And then there's all the quantum invariants, etc. And these have provided a very useful tool in knot theory and also in low-dimensional topology for understanding knots. And in around 2000, Kovanov had the idea. So Kovanov's idea was that all of these things here should be Euler characteristics of some homology theory. So Euler characteristics of something which has come to be known as link homology. So as the first example was Kovanov homology. So here you have, so this is a bi-graded vector space. Such that taking an Euler characteristic in one direction, so this is bi-graded Euler characteristic, yields things that we already know. And today, the focus will be on the categorification or the link homology belonging to the Homflip polynomial, which is called Kovanov-Lazansky homology. Or triply graded homology, or also Homflip homology. Okay, so you might ask, why would you like to do this? So there's another number of reasons. Firstly, it just produces more powerful invariants of knots. The second reason is that you expect it to be functorial under things like cobordisms, etc. And another reason is, in some sense, you'd like to understand what's happening here already. So,
what is the Q polynomial?
so here we have a bi-graded vector space, and we take an Euler characteristic along one column, but there's still an extra So it's something like, so here chi is something like alternating sums minus I dim k I j q to the j.
So is it correct to call it minor characteristic?
Well, it's summing in one direction. So yeah, if you have a singly graded vector space, then this is an Euler characteristic. Yeah. So that's why I say bi-graded Euler characteristic. But the general idea is that these things down here will have one extra degree of freedom to the things up here. So what I will attempt to explain in this talk is how equivariant constructible sheaves provide a natural setting for understanding some of these theories. That's the goal. So I need to introduce some machinery. So a kind of rough dream would be to say, okay, we start with a link, we construct some space, put a sheaf on it. The cohomology of this sheaf is this link homology. But this is unrealistic because these theories have lots of different gradings. So we need some way to get, lots of different gradings. And so the way we'll do that is by using some form of weight filtration. So that's the machinery I need to introduce now. So this will be some sort of black box equivariant and étale cohomology. So I want to recall very quickly étale cohomology. So if not étale cohomology, equivariant cohomology. If we have G, let's say a Lie group, then there exists a space EG, which is, so a space, so it's a G space, satisfying two conditions. Firstly, the G action is free, so G acts freely, or topologically freely, and EG is contractible. And then one defines, so the definition, so if we have X a G space, one defines the equivariant cohomology of G of X, as just the cohomology of X times EG over G. And this is the quotient by the diagonal action. So an example, if we take G to be C star, then we can take EG to be so an infinite vector space over C without the 0 point. And then, for example, the C star equivariant cohomology of a point is the cohomology of a point cross C star, C infinity without 0. Which is infinite projective space, which is a polynomial ring in one generator where X is of degree 2. So now I would like to, so we will use equivariant cohomology later on, but we need the extra gradings provided by the weight filtration. And so now I want to say that this has some kind of algebraic version. So recall, if we have X, so a variety over the algebraic closure of FQ, we can consider its Algebraic homology. So this is a graded K equal QL bar vector space. And the wonderful thing is that if X is defined over some finite field, then the Galois group will act on this. So if X is defined over FQ, then the Galois group of FQ acts on it, and inside here one has the Frobenius. And so I want to define Hij of X to be the Q to the J over 2 eigenspace of Frobenius inside the Algebraic homology. Okay. So in general, one will have other eigenvalues, but the situations that we consider are very simple, and so the only eigenvalues that ever occur are of this form. So I want to give you some examples of this. So if we take X to be P1, so in some sense the I direction is the cohomological direction, and J is the Frobenius direction. So here you have 0, 0, K and K. If X is the affine line minus a point, which is the multiplicative group, then one expects to have something here and here, because this is in some sense a circle, but in fact it doesn't live along the diagonal. So in general, if one has a proper space in it, then this will live along the diagonal. And I'll do another example in a second. So the last thing I need to say machinery-wise is that if we have G acting on X all defined over FQ, so we have some algebraic group acting on X, then one has the G equivariant Algebraic homology of X, and that this all has these. I'll need at one stage later on the equivariant derived category. So this has sheaf theoretic versions. So what I mean by that is that there exists a category called the mixed equivariant derived category. And an example is that if we take the map to a point, then P lower star of K of X is the G equivariant cohomology of X. So K of X, this guy is the equivariant constant sheaf. So this is all quite difficult to construct, but we only need that it exists. So you should think of this as analogous to the normal derived category. If you take the direct image of the constant sheaf, then you get the cohomology of your space. And so this is a version for equivariant cohomology. Okay, so now I can start explaining a little bit the connection to Lie homology. So I want to recall something called the Jones-Oceanu trace, which is one way that one can define the Hom-flipped polynomial. So I'll need some notation. So I'll erase this here. Oh. So I want to let Bn be the braid group on n strands. And inside Bn we have the generator sigma I. Which interchanges the ith and ith plus first strands so it's a positive crossing. And Hn should be the Hecker algebra over Z Q to the plus or minus a half. So this is generated by, the generators are the Ti for 1 is less than I is less than n minus 1. And the relations are Ti squared is Q minus 1, Ti plus Q, Ti Tj, Tj Ti. And lastly, the braid relation. And I think everybody knows the Hecker algebra much better than I do. But we have a very natural map from the braid group to the Hecker algebra, which sends sigma I to Ti. And on the Hecker algebra, there exists a trace, which I will define later on, called the Jones-Oceanu trace. Such that so I will abuse notation, and if I have a braid in here, I will just regard it as an element of the Hecker algebra via this map. So given any braid, sigma, its closure, sigma bar, is just obtained by closing it up like that. And that gives you a knot or a link. And it's a theorem that you can obtain all knots and links in this way. And if you apply... Sorry? Not just two, all of them. That's what dots mean. And if we apply this Jones-Oceanu trace to some braid, viewed as an element of the Hecker algebra, we get the Hom-flipped polynomial of the closure of sigma up to a factor. So up to a So up to q to the something times t to the something. And so now I want to bring in, so everybody in this room also knows what the Hecker algebra, kind of how the Hecker algebra first emerged. So I want to let G be GLN FQ. B be a Borel, and W is equal to the Weil group. Is equal to Sn. Now, after a specialization, this Hecker algebra is equal to B times B invariant functions on G with values in K. So after specializing and tensoring. And so under convolution. Now so now we've realized the Hecker algebra as some convolution algebra of functions on the FQ valued points of G. And so it's very natural to categorify this by the B times B equivariant derived category of G. So as an example of what happens here, in here Ti corresponds to the indicator function of the orbit BSB, where S is the simple reflection interchanging I and I plus 1. And under this categorification, that becomes the extension by 0 of this sheaf. And one can interpret multiplication here by push-pull, and so one gets a very natural convolution structure here. And just imitating this construction, one gets a map from the braid group up to here. And this is a very fascinating map, I think. So, for example, it's an open question as to whether this map is injective, whereas this is known to be injective. So the braid group really does sit inside this category. And so now it's very natural to ask, what does this Jones-Ocneanu trace mean in terms of this categorification? Now I want to recall one other thing, so I'll rub out.
I suppose this could have a kernel somewhere.
Sorry?
Bn into Hn has some sort of kernel.
Well, it might, yeah.
And then you have a problem for extending, defining the trace above.
But it's known that this is injective in some sense. So if two braids go to isomorphic objects here, then they're the same braid, which I think is a fascinating result. That's due to Kovanov and Seidel, I think. So in here, one has a very natural basis given by the intersection cohomology complexes. So and down here, they correspond to the Kazhdan-Lutzig basis. So I'll first describe what this trace is on this object. So I need one more piece of notation. So here we have B times B acting on G just by B1, B2 of G is B1G, B2 inverse. But inside B, one has the diagonal. And so if I write B delta acts on G, that means B acts via conjugation. So the first theorem is that if you take, so we can take the B delta equivariant hypercohomology of an ICBWB. So this will be some graded vector space, but by what I said before, it has two gradings, namely the second grading by weight. And so I completely forgot to define something before. What a pity. I'll do that now. Sorry about that. So so if we have a bigraded vector space, I want to define dim QT of this bigraded vector space to be the sum minus 1 to the I dim Hij q to the j over 2 t to the j minus I. So an example is at t equals 1. This is the so the alternating trace of Frobenius on the cohomology on the so some examples which will play a role later on. Dim QT of the cohomology of P1 is 1 plus Q. Dim QT of the cohomology of a multiplicative group is 1 minus QT. Dim QT of the GM equivariant cohomology of a point. So remember before I said that that the C star equivariant cohomology of a point was the cohomology of infinite projective space. And here you see this is 1 plus Q squared plus etc., which is 1 minus Q. So we'll see these factors coming up later on. So now the theorem is that the dim QT of this is exactly the Jones-Ocneanu trace evaluated on a CW. So
just as a question of interest, when you calculate this H cohomology, can you use cell decomposition?
Yes, certainly. So for example, if you take a Schubert variety, then this will exactly be the point counting polynomial of that Schubert variety. Or intersection cohomology, sorry? Point count, like just the, yeah. For example, P1, 1 plus Q. Things, yeah.
Are you sure about GM? Will the GM is each one, even if it's 1 minus Q, 1 half?
Yes, but so here we have, this is GM. So here, Frobenius acts by Q here. And so this will be, t to the 2 minus 1, which is t q to the 1.
You mean a prime there incidentally?
Probably. I mean, yeah, so. Also, I probably shouldn't write prime there. But
Should we know what trait the right-hand side is? Or you
I'll
assume
explain
that
it.
column
I'll
will
explain
work?
later. Yeah. At the moment, there just exists this trace, and I'll explain what it is later. Okay, so some remarks. The first thing is that this is a variant of an idea of Kovanov taking the Hochschild homology of Zergel bimodules. So this is a result of Kovanov. So this is Hochschild homology. So in some sense, it's a geometric translation of Zergel's idea of doing that. The second remark is in a 1987 paper, which is a very nice paper about the Hom-Flip polynomial, Jones asks a few questions. He asks, firstly, does TRN have a geometric interpretation? So geometric for him means something very different to geometric here, but the second thing that he asks is that can the KL basis be used? And the third thing he asks is that does TRN generalize to other types? So of course this definition works in other types and gives you, in some sense, a canonical trace. And so that's work in progress at the moment to understand that. And in particular, there's a definition by a Japanese mathematician of a trace in all types. And it seems at this stage that it's equal to this trace, but it's not yet proven. Still work in progress. So I want to explain now because up the top, in the top right-hand corner before, I said that we expect something triply graded. And at the moment, I've only explained 2 gradings to you. And so now I want to explain how to get the 3rd grading and how to define this Kovanov-Rozansky homology using this framework. So. So we start with L, a knot or link. And then by what I said before, we can find some sigma in Bn with the closure of sigma equaling our knot or link. And then that arrow there allows us to construct F sigma in D BBG. So from our braid, we're able to construct some B times B equivariant chief on G, or a complex theorem. And this F sigma has a natural weight filtration W. And so you can think we have some kind of filtered complex. And so this gives us a spectral sequence with E1 term minus P converging to the P plus Q equivariant hypercohomology of F sigma. And now, each one of these graded components will be a direct sum of intersection cohomology complexes. So you can think that this spectral sequence, the columns of it are what we have here. The columns of it are is the B delta equivariant hypercohomology of some intersection cohomology complexes. And so the spectral sequence is naturally doubly graded, but we have two gradings in each column, and so all pages of this spectral sequence are triply graded. So and so now you can analyze what happens as you pass from page to page in this spectral sequence. And at E1, E1 is invariant under, so E1 is almost a non-invariant, but not quite, is invariant under all moves except stabilization. I'm becoming an American. So I'll explain later what stabilization means. And also, using that theorem, one can show that the Euler characteristic is the Hom-flipped polynomial. And at E2 is invariant up to an overall shift. And is equal to Kovanov-Rosansky homology. So if you think passage from E1 to E2 will not change the Euler characteristic, and so we still have Euler characteristic equals Hom-flipped. And then the EI for I greater than or equal to 3 are also invariant. But it's not at all clear what their Euler characteristic should be, at least not to us. And 4, E infinity is E infinity depends only on the number of link components. So it's a very funny situation. You have a spectral sequence which converges to something very boring, and yet contains quite a lot of information along the way. So now I will explain, I will try to explain the kind of what's geometrically going on in this formula, and this is very simple. So. Yeah. Oh, so yeah, so so here I have another term. So each of these carries an extra grading. So just imagine that you have some spectral sequence, and the rows are operated on by some operator, and you take its eigenvalue decomposition. Eigenspace decomposition. Yeah.
That's supposed to be, because you left out the symbol, it's supposed to be the HIJ.
Yeah. No, it's no, because so it's so if you just take this guy will have two gradings. So I can't think now how they correspond in the spectral sequence. But it's certainly not true that the two gradings in the spectral sequence become the two gradings here. That's not true. So now, so I want to explain what the Jones-Oceanu trace is. So what they show is there exists a unique family of traces TRN from HN to Z Q plus or minus a half T plus or minus 1, such that, and now I'll write down the properties, the algebraic properties, and then go through and explain what they correspond to geometrically. So the first property is normalization. So that's that the first Jones-Oceanu trace is equal to this. The second property is that it's a trace. So this means TRN AB is TRN BA. So I should also, so what's that saying? That's just saying if I take the only braid in B1 and close it off, that's what I get. So this in some sense normalizes the unknot, the value on the unknot. This says if I take sigma 1, sigma 2, and close it off, that's the same as sigma 2 and sigma 1. The third thing is stabilization. which I mentioned before. So this has two parts. So we have an inclusion from the nth Hecker algebra and you want to relate the traces on the nth and the nth plus first Hecker algebra. And the first thing is that if I just include something, trn plus 1, that should be 1 minus qt on 1 minus q trn of A. And what's that saying? That is just saying that so here I have my braid sigma, and including it is just adding a strand, and then I'm closing it off. So this should be the same as the closure of sigma and an unknot. And we've already decided that the value of the unknot on the unknot should be this. And the second part is that trn plus 1 of tn, so this is the new generator of the Hecker algebra, times INA should be qt times trn A. And what's that saying? That's saying if I have my braid, qt, sorry. If I have my braid, I include it, and then I multiply by tn, and then I close. And that should be the same as, up to this annoying factor which we saw before, that should just be the same as closing sigma. Okay. So now, let's now I want to go through and explain kind of what each move means in terms of the formula up there. So what's this translate to? That translates to the multiplicative group acting on the multiplicative group, but the action is via conjugation. So it's a trivial action. So this is just the GM equivariant cohomology of a point tensored with the cohomology of GM. Okay? And as we saw before, that gives exactly that factor, and that gives exactly that factor. The second property, the trace, if I have two B times B equivariant sheaves on G. So multiplication in the Hecker algebra corresponds to convolution of sheaves. Yeah, exactly. Yeah. So all you have to do is check that this trace satisfies these properties, and then you're done. Oh, sorry. I possibly should have said that more clearly before explaining it for 10 minutes, but anyway. So we would like to compare the conjugation equivariant cohomology of this convolution with the cohomology in the other direction. But if you write down the definition of what this convolution means, this is just the B times B equivariant cohomology of the exterior product. So I'll get rid of that there. Give myself a bit more space. So this is, I have G and G, and I have B acting like this. Okay? And I have a sheaf here and a sheaf here. But this is, of course, the same as if I just turn them around the other way. Equivariant homology of G, F. And that's the, by the definition of convolution, that's the B delta equivariant homology of G involved with F. So that's why it satisfies this trace property. Lastly, so we need to check the stabilization properties. So for this we need two different groups. Oh, I should stop doing that. So here we need two different groups. We need GLN and GLN plus 1. We have the Borel inside there and the Borel inside there. And what one can show is that, I mean, it's not very difficult, is that if we have W in Sn, then this orbit closure is isomorphic to a multiplicative group times an affine space times BWB. So this implies that the, and this is an equivariant isomorphism. So this implies that the B delta equivariant homology of IC B prime W B prime is isomorphic to the GM equivariant homology of GM tensored with the B delta equivariant homology of ICBW B. And that is exactly giving the factor here. And that's giving the factor here. And this last property is very similar. You can check that. So this is equivalent to n plus 1 of 1 plus Tn, In of A, being 1 minus Q squared T on 1 minus Q times Tr n of A. And similarly, one checks that BWB bar, B prime WB bar, so again we have W in Sn. This retracts, so equivariant retracts onto SL2 times BWB bar. So this is this side. This is exactly the polynomial associated to SL2. And that gives you that factor. Okay. I'll stop a little bit early. Thank you very much for paying attention.
So this actually proves the existence also of the trace.
I guess so, yeah. I guess so. But it's not very difficult to show algebraically either. Exactly. So you look at how Hn plus 1 decomposes an Hn times Hn module.
But why is that difficult in other types?
Because it's just not true. This algebraic fact is not true. So, for example, Geck and Lamrapoulou have studied how many traces there are in other types. And for example, in Bn, there's a kind of, basically an infinite dimensional space of such traces. Like you have, at each step, So at each step, you need to fix an extra parameter. And so you have kind of countably many such traces. And so the question is to kind of single out one particular.
There's this sort of crucial thing here, B prime W, B prime closure, B...
That's all, this works in all types, yeah.
So in particular, the left side of the formula in that theorem makes sense in complete generality.
Yeah, and you can show it satisfies. So Geck and Numberpulu give a classification of traces in some sense. You can show it fits into their classification and has kind of properties that you expect.
Mm-hmm.
But still, their classification doesn't tell you a canonical one.
Mm.
And so that's what we're kind of working on at the moment.
Yeah, I suppose you could go beyond sort of Brouwer type decomposition, generalizations of these things. Too familiar with it myself. But instead of just having Brouwer decomposition, which has cell decomposition, there's a more sophisticated version. You could apply the same procedure, I suppose.
Possibly.
Any other questions or comments? So if not, let's thank Geordie again.